In the previous section, we introduced the electron's spin. Now in this one, we're going to talk about how the spin can interact with orbital angular momentum and the effect that has on the Hamiltonian and the energy levels that are observable. Let's start by reminding ourselves what the magnetic moment looks like that's due to the orbital angular momentum, or the m sub l. So we wrote that the orbital angular momentum vector takes this sort of a form in somewhat of a classical sense. Okay, using this, we can define a magnitude now. This is magnitude m sub l. Okay, and this looks like minus e over 2me. And now to simplify the expression for the angular momentum, we can write it as the square root of the magnitude squared of the angular momentum. And now we know what the eigenvalues of L squared look like, and so we can use this to simplify. And so this then turns into minus E h bar divided by 2 m sub e times L plus 1 square root. And using our previous definition of the Bohr magneton, this just becomes minus beta b, the Bohr magneton, times the square root of L times L plus 1. Okay, so this is an effective magnitude of the magnetic moment that comes from the orbital angular momentum. We'd be tempted to write the same expression now for the spin angular momentum, right? Because the spin angular momentum should have a similar form. We can choose the same charge and the same mass. But now instead of the orbital angular momentum vector, it's the spin angular momentum vector. This, however, turns out to be not quite correct. And what we need to do is we add this fudge factor, g. So this g it was originally called the anomalous spin factor because it couldn't quite be explained based on known theory up until Dirac's theory fixed all of that. Right, and now if we use this definition, then this gives us a similar definition for a magnitude. We'll use ms magnitude, which would be equal to minus g e h bar over 2me times square root of s times s plus 1. Or in other words, minus g times beta b, the Bohr magneton, times square root of s times s plus 1. And experimentally, you would end up showing that g ends up having a value of 2. And this is also a result that comes straight out of Dirac's theory. Okay, so now if you look at the magnetic moment that is caused by the spin that is pointing in the z direction now, this would be equal to minus e times g sz, so the spin in the z direction divided by 2me, then equal to minus g times the Bohr magneton times m sub s. Now, using the fact that m sub s is plus or minus a half, and that g was derived to be 2, this then tells us that we have two possible outcomes for the value of m as z. Or in other words, this tells us that the magnetic moment in the z direction for the electron that purely comes from the spin component can either be plus or minus the Bohr magneton. Okay, so this tells you that the electron spin results in an intrinsic magnetic moment. Okay, so there's an intrinsic magnetic moment coming from the spin. So this internal, purely quantum degree of freedom of the electron. There is also a magnetic moment coming from m sub l, or coming from the orbital angular momentum of the electron. And when you have two magnetic moments that are both present, just like two electric moments, like dipole moments, for instance, then these two magnetic moments will interact. And this is what's known as this spin-orbit interaction. So we can write the spin-orbit interaction Hamiltonian now in a similar way to what we did when we added in the magnetic field. We'll say that we have a new Hamiltonian H. And this is equal to H naught, which is our purely electric Hamiltonian. This is the one we started with, where we looked at the radial functions and derived the energy values. And then we add on this new term, which we're going to write like this. So there's a radial dependent term, and then there's this radial dependent term is multiplied by L dotted into S. So we can write this out more explicitly. This is the same H naught plus this complicated radial dependent term we're not going to worry too much about, and then times Lx hat times Sx hat plus Ly hat times Sy hat plus Lz hat times Sz hat. Okay, and into this last part here, this expanded inner product of orbital angular momentum with spin angular momentum, and this is the thing that is called the spin-orbit interaction. You can see that really what's going on is you have an interaction between the magnetic field created by orbital angular momentum with the magnetic field created by spin angular momentum. Okay, so unfortunately now, this equation is too complicated for us to solve exactly analytically. But on the plus side, this term is much, much weaker in its effect than the Coulomb interaction or the kinetic energy. And so, so to a very good approximation, we can consider that this is a near zero interaction, and that lets us use a theory called perturbation theory to estimate the energies or the effect of spin orbit on the energies without having to be able to solve this full equation exactly. This is the same perturbation theory we talked about with regards to the anharmonic oscillator, which gave us a form for the energies you get out of the anharmonic oscillator. And so the same statements we could make about the harmonic oscillator versus the anharmonic oscillator hold here. Perturbation theory will typically be pretty reliable if the perturbation, which is the spin orbit part, is small relative to the unperturbed part, which here is the hydrogen atom. And we'll see that the splitting caused by spin-orbit interaction is indeed a heck of a lot smaller than the energy levels we see from H naught. And so this will give us some way to validate that doing this through perturbation theory makes sense. But there's actually an even more important consequence of what the spin-orbit term does to the eigenfunctions than just changing the energies. It actually changes the symmetries. Because once you add in this L dot S term, then the Hamiltonian no longer commutes with just Lz by itself or Sz by itself. And this changes the nature of the solutions you get to the time-independent Schrödinger equation for the hydrogen atom. So the way that this is normally talked about is it says that spin-orbit interaction makes it such that m sub L and m sub S, the projections of angular momentum and spin onto the z-axis, are no longer good quantum numbers. And now in the next video, I'll tell you what I mean exactly by something being a good quantum number. And we'll use that to explain why L and S are no longer good quantum numbers once you have spin-orbit interaction, what is a good quantum number in these systems, and then this will give us the opening to start talking about spectra, because knowing what are good quantum numbers is the first step to knowing about selection rules.